Alright, so we're ready for section 7.3, titled the Central Limit Theorem for Sample Proportions. Right, so the two big things we want to do here: identify the conditions needed to apply the central limit theorem for proportions, and also be able to use the central limit theorem for proportions to describe the sampling distribution of a sample proportion and to find probabilities. Right, so remember the central limit theorem allowed us to know within one standard deviation, 68% of our data would fall, within two standard deviations, 95%, and within three standard deviations, 99.7%, right? So that's still going to apply here if we meet some conditions. So the central limit theorem for sample proportions, we're going to use this to estimate proportions in a population, and also to tell us that if some basic conditions are met, the sampling distribution of the sample proportion is close to the normal distribution, right? So if we take a random sample from a population, and if the sample is large enough, and if the population size is much larger, then the sampling distribution of p hat is approximately normal with a mean of p and a standard deviation of the standard error, right? So, and if we don't know the value of p, we can substitute in the value of p hat, right, to get a close estimate. Right, so my mean is going to be p, and my standard deviation is the standard error, right, which we looked at in last section. So here are the three conditions that the book suggests for the central limit theorem. So one is that we need my sampling to be random and independent, right? The next is that we need a large sample. So the sample size n is large enough that the sample expect at least 10 successes and 10 failures, right? So in other words, if I take n times p hat, that should be greater than or equal to 10, and n times 1 minus p hat has to be greater than 10. Or in other words, n times q hat, right? So remember, I introduced q to you, which is so p is used for successes, right? But q is the proportion of failures, right? So also we need a big population. So if sampling is done without replacement, the population must be at least 10 times larger than the sample size, right? So we have to see, does it seem reasonable for my population to be at least 10 times the sample size? Right. So here is a figure. So we're told that we have a sampling distribution of p hat for 10,000 samples of size 10 drawn from a population with p equals 0.25, right? But note here that this does not satisfy condition 2. The sample size is too small, right? If I take p hat times my sample size of 10, I'm not going to get that bigger than or equal to 10, right? So thus the distribution does not look to be normal, right? It's looking like it could, looking more like a right skewed distribution. So here's another example where we have a sample size of 100, right? So we have distribution of p hat for 10,000 samples of size 100 drawn from a population with p equals 0.25. Right, so we looked at an example of this, remember last time, where 0.25 are cat people, right? So it's just drawing on that example. So note that this does satisfy the sample size condition now of the central limit theorem, and the shape of the distribution is approximately normal, right? So this red curve would be the normal curve, and you can see the histogram follows that pretty well, right? With the mean being in the center. So the standard deviation, or in this case we call the standard error, is calculated by taking p hat times q hat divided by your sample size, right? Or excuse me, in this case we're using p and q, right? Not p hat and q hat. So we can use those to estimate, but we don't need to because we do know p in this case, right? So we get a standard error of 0.04. So here's another example about vegetarians. So according to the statisticbrain.com website, 59% of vegetarians are women. So let's suppose that we have a random sample of 500 vegetarians. What is the approximate probability that the proportion of females in our sample will be more than 63%? So the first thing you always want to do before we can apply the central limit theorem is that we need to check our conditions. So the sample was random and independent, right? So then we need to check our sample size. So check n times p and n times q and see if that's bigger than or equal to 10, which it is in both cases, right? So you can see those calculations. And then we need to check, can we assume that there's at least 10 times 500 vegetarians in the population? And yes, right, that seems to be a fair assumption, right? That there's at least 5,000 vegetarians in the population. So since these conditions are met, then we can assume that the distribution will be approximately normal, and here's my standard deviation, right? So we're plugging in 0.59 in for p, right? And then q is 1 minus p, and then dividing by n, which is 500. Take the square root of that, and we get 0.022, right? So that's my standard error, or essentially my standard deviation, right, which we've talked about. So to find the probability that the proportion in the sample is greater than 63%, we can use technology to find this, right? So here's actually a printout. I believe this is from StatCrunch. But we have to be able to do this on the calculator, right? So let me just remind you how we would do this in the calculator. So you would go to second and then distribution, and we want normal CDF. And then in the lower, you would put 0.63, right, as I have here. The upper, we're going to go to infinity, so how we can code that is 1E99. And remember how to get the E. You hit second and then this button here, the comma, right, this EE. That gives you that correct E that you need for scientific notation. My mean is 0.59, right? My standard deviation is 0.022. And if I go down and hit paste, it'll type it in correctly and hit enter, and our p-value matches, right? So that's the area under the curve, which is the probability, right? That will have something bigger than 63%. So here's another example with voting. So in a closely contested school bond election, polling indicates that 50% of voters are in favor of the bond and 50% are against the bond. So suppose that we have a random sample of 80 voters. So we want to answer these 4 questions. So what percentage of the sample would we expect to favor the bond? Does the central limit theorem apply? What is the standard error for the sample proportion? And then if so, what is the approximate probability that the sample proportion will fall within 2 standard errors of the population value, p equals 0.5, right? So going through each one of these, number 1, right, I was saying because we have taken a random sample, we expect the sample proportion to be about the same as the population proportion. So we expect 50% favor the bond, right? So since we have a random sample, we're assuming that p and p hat are going to be similar, right? So we have a random sample, n times p equals 80 times 0.5, so we get 40. And n times 1 minus p, or n times q, we get 40 also. So since 40 is bigger than or equal to 10, our sample is large enough, right? We will assume that there are more than 800 voters in the district, right, which seems fair. So all the conditions are met. So if we plug in p and n into our standard error equation, we get a standard error of 0.0559. Right? And since the central limit theorems, we can use the normal model for the distribution, right? So here's my normal model, here's my mean, there's my standard deviation, right? So by the empirical rule, we know that the probability that the sample proportion will fall within two standard errors of 0.5 is 95%, right? We could also verify this using technology. Right? So we could go to second distribution, go to normal CDF. My lower bound is 0.6118. My lower bound is 0.3882, right, as calculated here. My mean is 0.5. My standard deviation is 0.0559. So go down to paste. And getting a negative value, that doesn't make sense, right? Did I enter something in wrong? Let's check. I have the lower and upper flipped, right? The lower bound should be 0.3882, right? So you guys are probably yelling at me that I was doing that backwards. So the upper is 0.6118. Then we have the mean 0.5, right, and the standard deviation of 0.0559. So now we should get that correct, right? Yep. So we get 95%. So the key idea is if the conditions for the CLT are met, the probability that a sample proportion will fall within two standard deviations of the population value is 95%, right? So within one standard deviation is 68%, and then 95%, and then three standard deviations and 99.7, right? Just like we've done all along. Right. So here's another example of dog owners. So according to the American Veterinary Medical Association, 36.5% of all Americans own a dog. Suppose a random sample of 200 Americans is taken. Would it be surprising to find that 45% of the sample owned a dog? Why or why not? Right? So we want to use the idea of central limit theorem here to investigate, does that seem unlikely, right? So first of all, of course, we need to check the conditions. So number one, we have a random independent sample, so we're good there. If I take n times p and n times q, I'm getting results much bigger than 10, right? So we're good there. And then my sample size is 200. If I know I can definitely assume that more than 10 times of that will be the population, right? So we're good there. So we can go ahead and calculate the, so we can assume that the distribution of sample proportions will be normal. So we can go ahead and calculate the mean, right? The mean here would be equal to p, and the standard error is calculated by the following, right? So there's my standard deviation. So if I take the mean plus two standard deviations, right, I end up getting 0.433, right? So 45% is more than two standard errors from the mean, so it would be very surprising, right? 95% of my data is going to be in between two standard deviations. So something bigger than that would be very surprising, right? Right. All right. So that's all I have for this section. So we're just learning about how we can take a sampling distribution of p, right? So we have the sampling distribution of p hat, and how that can, if certain conditions are met, then that's going to be approximately normal, and we can apply a central limit theorem, right? That's where it's really powerful in this section, right?